Energy, the true currency of the 20th century. Today, we as a nation use energy in our homes to provide an attractive and varied lifestyle. We've become accustomed to the conveniences and comforts that energy provides. Historically, homes provided little more than shelter. Some comforts were achieved with little energy use. However, after electricity became widely available, housing began to change in design and function. Simple shelter evolved into structures of artificial environments, air conditioning, lighting, food preparation, personal hygiene, recreation. Today, the average Florida homeowner spends approximately 70% of every energy dollar to operate air conditioning, space, and water heating. Since the 1970s oil embargo, Americans have become aware of the benefits of energy efficiency and conservation. Advances in designs and technology have allowed us to reduce our energy use without sacrificing our lifestyle. Energy expenditures, however, have continued to rise. Residential energy consumption represents 25% of all energy used in Florida by all energy users. When building a house today, energy efficiency can be achieved through passive and active approaches using readily available off-the-shelf technology. Passive approaches include designing for solar control and selecting mechanical systems which do not require energy to operate. Active methods refer to systems which require energy to operate. The designer's goal is to reduce energy use through appropriate passive methods and by selecting equipment that is energy efficient to operate. Let's look at how an energy efficient home can be constructed. This is the home of Dr. and Mrs. Dwight Adams, located in Gainesville, Florida. When the Adams decided to build a new house, they made a commitment to achieve the highest level of energy efficiency possible without sacrificing lifestyle or comfort. The passive design approaches used on this home include the control of solar heat gain through orientation of the house on the lot, window type and placement, shading devices like roof overhangs, thermal buffering and storage, radiant heat barrier coating, ceiling and wall insulation, passive ventilation, infiltration control, water-conserving plumbing devices, radon control, enviroscaping. Let's look at each of these items. Through strategic planning and design, the house was oriented for optimal control of the sun. In Florida, keeping out solar heat during the summer is a prime consideration. The best orientation typically places the longest walls facing north and south, which minimizes the wall's direct exposure to the sun's rays. Windows are important for daylighting and other purposes, and can also affect the amount of heat that enters and leaves the building. The architect chose a double-glazed window system with an aluminum frame to ensure a tight and durable window unit. These windows are manufactured with a thermal break in the frame which reduces heat loss or gain by conduction through the frame. 3-foot overhangs and strategic window placement reduce the solar heat gain by shading the windows. The architect buffered the main living spaces with infrequently used rooms, such as the foyer. This design feature provides extra insulation from the sun for high-usage areas. Different types of floor systems were also used to manage the sun's heat. Slab floors were placed on the south side of the house to take advantage of thermal gains during the winter. In this example, the porch slab is shaded during the summer by the roof, which minimizes heat buildup in the slab. This heat could radiate back into the house, adding to the heat load, which increases air conditioning use. During the winter, however, it captures and stores the sun's heat, which can be radiated back into the living space. This can reduce the demand on the heating system. Another important passive feature is the radiant heat barrier coating that was sprayed on the underside of the roof deck. This coating reduces the radiant heat transferred from the roof to the conditioned space by approximately 80%. In the summer, air conditioning savings of 8 to 15% are possible. In the winter, heating costs can be reduced 2 to 5%. In addition, the radiant barrier can effectively extend the fall and spring season. This extends the time that the heating and cooling system can be left off. This can save an additional 12 to 20% annually. Properly installed ceiling and wall insulation is crucial to achieving satisfactory levels of energy conservation. It is very important that the insulation be installed tight against the framing. Gaps will allow heat to enter or exit the building. In Florida, the spring and fall are often comfortable enough outside that heating nor cooling is necessary. During these times, indoor comfort can be achieved by simply opening the windows and letting the outside air in. Cross-flow ventilation and convective ventilation are passive ways to move air freely through the house. Cross-flow ventilation is achieved when windows on opposite sides of the house or room are opened, so air can flow across the space. Convective ventilation is achieved as warm air rises. In this tall central space, the warm air rises and flows out the windows at the top. As the warm air exits at the top, cooler air is drawn in at the bottom of the space. This natural convective airflow can produce a comfortable environment without the need for air conditioning. Unconditioned, humid air infiltrates into a house through cracks or openings. These penetrations through the wall, ceiling, and floor can significantly affect energy use. During construction, the contractor minimized unwanted infiltration by 1. Sealing the joints of the subfloor plywood sheathing with butyl rubber caulk, 2. Caulking the bottom plate of the exterior walls with 2 beads of butyl rubber sealant, and 3. Sealing all holes and penetrations in the bottom and top plates with a fire retardant sealant and applying a foam sealant around all windows and exterior doors. The exterior wall was constructed to create multiple infiltration barriers. A half-inch plywood structural sheathing was first installed, and then an infiltration barrier was placed over the plywood. Finally, a plywood finish sheathing was installed over the infiltration barrier. On the interior, the sheetrock was also sealed to the top plate with a flexible sealant. This sealant and additional nailing along the top prevent air from moving between the attic and the wall cavity. And finally, all electrical boxes and other sheetrock penetrations were sealed. Water-conserving plumbing fixtures and controls were selected for this house. Low-volume toilets and flow restrictors in shower heads help prevent wasting water, especially hot water. Pumping, heating, and distributing water in the home and the disposing of wastewater are all energy-intensive activities deserving consideration. When radon gas accumulates inside a building, it can create a very unhealthy environment. In new construction, radon entry can be controlled at little cost. Radon is prevented from entering the house through the slabs by creating a barrier under the floor. The plastic membrane vapor barrier was installed with all lap joints and penetrations taped and sealed. A 2-inch layer of sand was installed over the plastic sheeting to protect it from being torn by the wire mesh reinforcing. The sand also enhanced the curing process, which results in fewer cracks in the slab. Another radon control technique is shown here, being installed under the garage slab. A subgrade drainage mat material was laid down before installing the vapor barrier. The mat allows for the soil gases to be more effectively collected. Then they are vented to the outside using PVC piping routed through the wall, attic, and finally through the roof. Landscaping that is time and resource efficient is called enviroscaping. It involves using native species of plants and shrubs, often mulched with yard trimmings, bark, and compost products. Enviroscaping not only increases the aesthetic value of the property, but can reduce energy-intensive maintenance. Strategically chosen and placed plants provide shade in the summer and can buffer the house from cold winds during the winter. Plants that are not native to a particular climate often require more care, more water, more chemical fertilizers and pesticides, all energy-intensive inputs. The active design features used on this house include a ground source direct exchange heat pump, a programmable electronically controlled multi-zoned air distribution system using an acrylic-coated ductboard, a desiccant wheel energy recovery ventilator, an electronic air filtering and cleaning system, energy-efficient appliances, energy-efficient fluorescent lighting, and a waste heat recovery system for heating water. A unique feature of this house is the heating and air conditioning system. Multiple computer energy analysis were conducted on the house's design by a local energy specialist. The analysis helped in the selection of the heating and cooling system. The system selected is a relatively new type of heating and cooling system, the ground source direct exchange heat pump. While this system is used frequently in the north, it is now gaining popularity in Florida. While operating as an air conditioner, the system relies on the temperature of the ground to dissipate heat from the condenser coils. Traditional air-to-air heat pumps use fan units to blow air across the condenser coils to dissipate the heat. Not only are these traditional units noisy, but they also produce a lot of additional hot air. Also, for standard heat pump systems, the compressor condenser coils and fan unit are located out of doors where the weather, insects, and debris can cause various maintenance problems. The ground source direct exchange heat pump selected for this project required the installation of 1,000 feet of copper tubing, a minimum of 4 feet below the ground. These copper loops dissipate the condenser heat into the soil. The ground loops are connected to the compressor located inside the building. By moving this part out of the weather, less maintenance is required. Also, no fan motor means no noise, no hot air, and less maintenance. Energy savings of 40 to 60% are realized with this system as compared to traditional systems. Now the conditioned air must be moved throughout the house. Usually this is accomplished with a duct system which branches into each room. When a traditional air conditioning system is running, air is delivered to all rooms simultaneously. Normally, this type of system has only one thermostat and therefore will not respond to temperature differences within the house. Here in the Adams house, multiple thermostats and electrical dampers direct the conditioned air to those spaces in the house where needed. This means that you are not heating or cooling the entire house every time the system comes on. By supplying conditioned air only to those spaces that need it, less energy is required to maintain comfort. As air moves through a duct system, it picks up particles and fibers off the surface of the duct, then carries them into the living area. Other substances like molds and fungi can grow inside the ducts and cause indoor air problems. To reduce this health impact, a new ductboard material coated with a permanent biocide was used. This coating also provides a more durable interior surface that can withstand cleaning without damaging the lining. A major consideration in an energy-efficient building is the balance between the tightness of the envelope and indoor air quality. A tight building reduces the amount of fresh air normally introduced through infiltration. Without the proper amount of fresh air, an unhealthy accumulation of gases, odors, and germs can result. When infiltration is reduced, indoor air quality is maintained via the air conditioning and heating system. Since this house is sealed against uncontrolled infiltration, a desiccant wheel energy recovery ventilator was prescribed as part of the heating and cooling system. This piece of equipment allows for inside air to be replaced with fresh outside air at a controlled rate. It also reduces the energy penalty by extracting some of the moisture in the incoming air with a desiccant. The ventilator also allows for heat transfer between the incoming and outgoing air streams, thereby reducing the demand on the heat pump by preconditioning the outside air. This process saves energy and provides a more comfortable and healthy environment. Working with the energy recovery ventilator is an electronic air cleaner and filter system. This equipment is installed directly into the duct system where it removes even minute airborne particles. Together, these units keep the air fresh and clean, further assuring a healthier and more comfortable environment. Dr. and Mrs. Adams chose to use natural gas for the range, oven, and clothes dryer. For these appliances, natural gas has proven to be the most efficient energy source. And natural gas is environmentally friendly since its emissions contain less greenhouse gases and air pollutants than coal or oil-derived energy. Fluorescent lighting was chosen for most of the lighting needs because it produces more lumens per watt of energy than traditional incandescent lighting. This produces less heat for the air conditioning system to dissipate. And as an added bonus, they last longer, save on installation time, and are generally more cost-effective. Hot water can be expensive to produce. Electric water heaters often represent 30% or more of an electric bill. A heat recovery unit can take advantage of the heat generated by the heat pump in the AC unit and use it to heat water. This produces free hot water when the heat pump operates. The heat recovery unit also increases the heat pump's efficiency by pre-cooling the compressed refrigerant. The heat recovery unit is a passive device. It has no moving parts to wear out, nor does it have any other energy-consuming components. These active systems working together with the passive design features produced a home with an energy performance index of approximately 30. Currently, to qualify under Florida's Model Energy Efficiency Code, an EPI value of 100 or less is required. This level of energy efficiency was accomplished with off-the-shelf technology and without a radical departure from traditional aesthetics.
We've been living in the house about 6 months now and are really enjoying it. As you can see, the house was designed for the comfort and pleasure of the occupants, and we are finding that we really enjoy living in the house.
I really like all the natural lighting coming through the windows. I don't have to go through the house turning on the lights all during the day.
One of the nice parts are the utility bills. Our electric bills for the months during the winter have been exceedingly low. Our total heating bill for the winter has been only about $200, so from that standpoint, it's really been worthwhile, and we're really enjoying all aspects of the house.
If we look back over the past 20 years, we can see that energy use has risen at a steady rate. Because of this, owning and operating a house is becoming more expensive. We are also learning more about the environmental and social costs associated with excessive energy usage. Consequently, any action taken to minimize the energy used in a home while maintaining comfort and lifestyle requirements can be a real help to the family, community, and the environment. Lending institutions are beginning to understand the value of energy-efficient construction. They recognize that a modest investment in installation costs can lower operational costs. Some are even adjusting their qualifying criteria to reflect an increased ability of the homeowner to pay the mortgage. Builders also recognize the value of how energy-efficient technology can increase the market for their homes. And let's not forget that money saved is worth more than an equal amount earned. Energy-efficient construction pays for itself. We urge you to explore these ideas and technologies with your builder or realtor and help pioneer an energy-efficient 21st century. For more information on energy efficiency, contact the County Cooperative Extension Office, your Energy Information Center.
The Energy Extension Service receives funding from the Florida Energy Office, Department of Community Affairs, and is operated by the University of Florida's Cooperative Extension Service.